right? So, so S is coming over and from for the cubic power, you can say is from, I mean, you can start from anywhere. So one infinity, and then the odd to m minus one, right? Oh, but it's alternate. Or it makes, I mean, that is, I mean, you can still use one, but then because the first term is positive, so it's n plus one. Well, make it even. I mean, not even. It's just alternate. So start the positive term because this is odd. So one is, yeah, I think so. Yeah, this is the S, right? Do you get the same S? This is the sum that you wanted to do, right? And so you compare the form. Uh, this is, I mean, you could, it looks like there's a one half. You can that make you think that you might use the, the either the third one or the fourth. It's alternate, so you you might use the fourth one. I'm looking at table 11.2, right? Except that it's not quite a four. Maybe we can start from zero. Then it's 2n plus 1. And get rid of that. So you get similar form. So this is like putting the 2 out of the integral. So you get 2 to the third power 1/8. And plus 1/2 to the power. Right. So that's like the form in the fourth formula in the table 11.2. Well, you could try. Anyone try this? Haven't got into this. This is 11 homework 11.9.3, right? Did I get this right so far? So first you could now you need to extend it to minus infinity to infinity. The one thing to do is like the first trick is n to minus n. Right. If treating is minus, that would be n from 0 to minus infinity, and minus n and minus n doesn't matter, right? It's become minus n, they have the power. And to put it in the same form, you probably need to shift to n also, because you want to start from, I mean, you can move it to minus infinity to 0. You want to actually shift it down to just minus 1 because you already have a 0. And then this is not quite right, this 2, right? And so you need to change n to n minus n to n plus 1, so you get minus sign. The minus sign plus 1/2 in minus 1/2, that becomes the same form. So basically, you want to change n to n plus 1. In that case, the new n will be the old n minus 1, so you stop at minus 1. Okay. So the shift it to now you change it to the new n. I mean, this is a little confusing sometimes doing these things. But it's the new n will stop at the old n minus 1, so step minus 1. So now the old n is n. 1. This becomes minus n minus 1 plus 1 has a minus n minus 1 half to the power. And there's a minus sign in the denominator. Cancel a 1 minus sign in the numerator. Yeah, put it in the same form. So that's exactly the same. So the S is this one. So you see that do you follow this? Did I do it correctly? Are you following me? So this one is exactly this one. Not exactly. This the form exactly, but the sum over minus infinity to minus 1. But combining the two will give you the full summation from minus infinity to infinity, except that you need to divide it by 2. 16. Now this is the form in the fourth formula, and you can just cite the formula. And this is sum over all the residue at of the residue of fz pi secant pi z, and our fc is, I mean, of course you need to carry the coefficient because it's the coefficient, and the function f is now just this one without the whole thing called z. We're comparing the formula, right? Compare with the formula. So this 1 over c cubed, 1 over c cubed times pi secant at the pole of the f, which is this c, the f. Right? Is it okay? So, and there's no sum, it's just one pole, right? And this is a cubic pole. Yep. So a cubic pole, which means you need to do the derivative, right? So let's see, A16, and remember for last time we did that, d squared dc squared, right? And then multiply CQ, right? Multiply CQ cancel with that. And what is left is just, there's a pi, we can take the pi out, sequence pi z, evaluate at sequence here. And then there's a normalization. It should be 2 factorial, right? Is it? It's Q. Okay. See that again? Yeah, there's a q c cube. The formula is multiplied by c cube, right? And then take the second derivative of the rest of the function, right? Because you multiply c cancel with this c cube. The rest is just this secant, right? And then take the second derivative divided by the normalization. That's the third order pole. Formula for the residues for the third order pole, right? Now you just the usual thing, you carry out the derivative. I mean, you can use look up the derivative and then do straightforward derivative. I mean, secant, and the secant is 1 over cosine. That you probably can do. And then another trick I did that. you can just do a Taylor expansion of the, because we're taking derivative and then finally we set z equals 0. We take a Taylor expansion of around about z equals 0. You keep only up to second order in z, then the coefficient of the second order term uh, will give you the derivative that you use. That will give you a constant after you take second derivative, and then whatever coefficient multiplied by the I mean, take a derivative, you get a factor of 2 out. Right. That you can also do it that way also. So that it is fast enough. It's 60. Let's keep at this screen. And this is secant is 1 over cosine. And do power series. Cosine is 1 minus the argument square, the pi square c square, divided by 2 factorial, which is 1/2. Right. And then next step you can, I mean, there's I order term. This is fourth. C is fourth. The next step is C fourth. We do the binomial expansion basically inwards that. Basically, that becomes basically that. Put it in the numerator as a cancel this and change it to a plus sign. Right. And second derivative will be just taking the derivative of this c squared term, would give you a factor of 2, cancel the factor of 2, right? And that should be it. So altogether, it's just this derivative, second derivative will give you pi square. So pi square, pi cube, and cancel the 2 with the derivative, and then altogether is 32. Did the question has the answer? No? Did you get there? Some people, did you get this answer? Just want to check whether this, like, anyone has the answer? No? No? No. Yeah, you got the same answer as this one? Okay, okay. Let me just save it. I can actually look that up. Oh, yeah, got this. I look at the one page. 11 from 93. What did that before? Yeah, pi cube over 32. Yeah, okay.